So today's talk is going to be about a concurrency toolkit that we're proposing for the C++ standard. It follows on as a natural ordering after that you have share pointers, and then, of course, atomic share pointers from C++ 17. Well, not exactly. I guess it's in the concurrency TS, so it's not really in there yet, but it is in the concurrency TS. And the follow-on after that, we think naturally is something called hazard pointers and read, copy, update, RCU. I'm going to skip past most of these things. I'm essentially giving you a kind of a high-level motivation, and then we're going to be followed by the actual authors of hazard pointers and RCU coming up to explain what these interesting objects are. But the agenda today is essentially we're going to start with something of a play on words. Erwin Schrödinger's zoo and Werner Heisenberg's advice. That increased uncertainty can get you performance and scalability. So as a result, given that knowledge, procrastinate away. And one way we're going to do that is by using structured deferral. And we're going to take a look at a table that we've been working for over 2 years, comparing the various features and properties of share pointers, atomic share pointers, versus hazard pointers, and read, copy, update. And then finally, Maggot's going to come up. He's the author, the inventor of hazard pointers, and Paul McKenney is going to come up, and he's the author and inventor of read, copy, update, and explain the fine details of that. And we're going to finish that with a conclusion that this is appropriate, with this along with atomic share pointer and share pointer, forms the beginning of an appropriate concurrency toolkit for C++. So Erwin Schrödinger would like to construct an in-memory database to keep track of the animals in his zoo. This is a thought experiment, just like many things in physics. I have a background in astrophysics, so I like these kinds of thought experiments. Birds would, of course, result in insertion into this database, but deaths would result in deletions. The database is also queried by those interested in the health and welfare of Schrödinger's animal. Schrödinger has numerous short-lived animals like mice, resulting in high update rates. In addition, there is a surprising level of interest in the health of Schrödinger's cat. So much so that Schrödinger sometimes wonder whether his mice are responsible for these many, many queries. Is the cat still alive? Is it still alive? Is it still alive? So regardless of the source, the database has to handle a large volume of cat-related queries without suffering from excessive levels of contention. Both accesses and updates are typically quite short, involving accessing or mutating an in-memory data structure, and therefore synchronization overhead cannot be ignored. So Schrödinger also understands, however, that it is impossible to determine exactly when a given animal is born or dies. For example, suppose that his cat's passing is to be detected by the heartbeat. When the heartbeat stops, it's dead. Now we use instruments to do that, and of course seconds or even minutes would be required to determine the poor cat's state of health. So the shorter the measurement interval, obviously, the less certain the measurement. So that a pair of veterinarians might examine a cat and would disagree on the exact moment of the cat's death. For example, one might declare the death 30 seconds after the last heartbeat, while another might insist on waiting a full minute, in which case the veterinarians would disagree on the state of the cat during the second half of the animal, second half of the minute after the last heartbeat. Fortunately, his good friend Werner Heisenberg has taught Schrödinger how to cope with these kinds of uncertainty. The delay in detecting the cat's passing actually permits use of synchronization via procrastination. We all like to procrastinate. So after all, given that the two veterinarians' pronouncement of death were separated by at least a full 30 seconds, a few additional milliseconds of software procrastination is perfectly acceptable in this case. So in fact, Schrödinger's design goes further by actually exploiting the ambiguity and uncertainty. He does this by refusing to require that queries and insertions and deletions be fully ordered. As we will see, this design choice is going to enable extremely high-speed queries. So now, if we step back to real life, this situation is not limited to Schrödinger's zoo's database. Any situation in which data within a computer is a function of events and entities outside the computer, for instance, similar uncertainty will be enforced by the speed of light delays. By the time a given change has been committed to the system's memory, it might well have been superseded by some other change. It might not even be possible to determine the time order of several external events. If the sun, for instance, explodes this very minute, we would not find out about it for another 8 minutes. Okay. Worse yet, these are situations where protocols introduce additional delays. For example, such delays are common practice in internet routing protocols. These routing protocol delays are absolutely necessary because we have to use it to preserve internet stability. However, they do introduce long periods, and this is the key, during which a given system connected to the internet might be uncertain of the internet's topology. The applicability of unordered lookup is now quite broad, if you follow this analogy. So suppose that an algorithm uses the common idiom that makes a decision while holding a lock, then relies on that decision after releasing the lock. This algorithm is in fact relying on obsolete information because some other CPU might have acquired a lock and change the data on which the decision was based, while the first CPU is still relying on its now obsolete decision. In short, synchronization via procrastination is especially useful when interacting with external states. So given that knowledge, we've actually looked at a number of algorithms, and we've already had something called, it turns out that there are 4 key approaches. There might be more, but right now I just only want to talk about 4 that can resolve this problem. One is actually a fairly common idiom using reference counting, and indeed that's what sharepointer does. The other one is something that we added to the concurrency TS called atomic sharepointer, using double compare and swap reference counts. Now, this was quite interesting. This took our group quite some time to discover until I talked to Anthony Williams and found out he's pretty much the only one who was able to implement atomic sharepointer end-to-end using truly atomic increments at reference counting as well as reclamation. The Boost one claims it does it. The Boost atomic sharepointer claims it does it, but it doesn't really do reclamation fully. We talked to Peter Demoff about that as well, too. So we can see how challenging this is. I'm going to talk a little bit more about that. But the third and fourth part are the really interesting part. We now have these two toolkits, additional toolkits, hazard pointers, and recopy update, which we're going to offer up to the C++ standard for standardization for inclusion into the concurrency TS, which means that it could land in C++ 20. So in short, what I'm saying is that synchronization, which is via procrastination, which is the commonality of all these patterns, is especially useful whenever you're dealing with external state. Okay? So to see how this is a common idiom. I've talked about the basic problem ultimately is just about the finite speed of light. And of course, the fact that atoms and electrons that carry our information can't really move any faster, even though they've been moving at the same speed every time. Now we're saying, God damn it, you gotta do it faster. So just a little bit of recap. You know about the C++ 11 smart pointers. They're error prone. This was one of the primary reasons why we added to them for atomic share pointers. Now, some people think that it was just syntactic sugar that we added that atomic share pointers. It wasn't. With the original share pointer, it's somewhat inefficient because atomic compare exchange strong is a free function taking a regular share pointer. And we don't want extra synchronization in share pointer itself. So this slide I actually took from Anthony Williams' blog, which I thought was really nice. A simple solution for Schrodinger's cat's Schrodinger's zoo is to place a reference counter, of course, in each animal's data element within a hash table, with collisions handled by chaining. So the readers atomically increment and reference, these are the mice, before accessing animals' data elements, and atomically decrement it afterwards. So this provides synchronization only between readers and updaters. Updaters have to synchronize among themselves using other alternatives, using other mechanisms such as locking, non-blocking synchronization, or even transactional memory, something I'm fairly familiar with. So here in this particular example, the std share pointer works great if there's an instance of it in every thread, so that changes to the reference count are synchronized. Everything just works if your shared data is correctly synchronized. You would need to ensure that it's safe to call, in this particular example, according to Anthony Williams, and we agree, that it's safe to call my class do stuff and do stuff with from multiple threads concurrently on the same instance, but the reference counts are handled okay. However, the minute you move to, some of the words are moved over, but that's close enough. So here I want to look at what this really means. So when you have deferred reclamation via reference counting. What you're doing is you're combining waiting for readers and multiple versions. So the four-state process of removing the data element corresponding to Schrodinger's forecat is shown here. The initial state here shows one chain of the hash table, representing Schrodinger's boa, cat, and GNU. As indicated by the red color of each box, any number of readers might be referencing these data elements. So therefore, updates has to be carried out carefully to avoid disturbing these readers. To transition to state 2, the updater stores a pointer to the GNU's data element in the next pointer of the boa's data element. So this store has to be atomic in the sense that any concurrent reader has to see either the old value or the new value, not some mashup of the two. So such a store might be carried out using a C++11 relaxed atomic variable or an older compiler, some sort of volatile cast. Know that the cat's next pointer continues referencing the GNU's data element to accommodate readers still referencing the cat. So from this point onward, there is no path to the cat's data element indicated by the yellow color, okay, at which point we're waiting for reference to drain. So now readers cannot gain access to it once the cat's reference counter reaches 0. Transitioning to state 3, all the readers that had a reference to the cat's data have to release their references, indicating by the green color of the cat's box. And because there's still no path to the cat's data element, new readers still cannot gain a reference to that. Okay? So going back to why we needed atomic share pointers, it turns out that if you're going to access this from two threads, the share pointer from two threads, you have really two choices. One, you could wrap the whole object with a mutex, so only one thread is accessing the list at a time, a big hammer. Indeed, this is what you have to do with the standard library if it's not thread safe. So we could also try and allow concurrent access, but there are problems. These problems, I'm not going to go into them because it's quite broad, such things like removing from the front of the list, the race condition on the head, or multiple threads calling pop front. Although, interestingly, it doesn't suffer from the ABA problem. But with atomic share pointer, it turns out that it can guarantee atomic access. It can be implemented more or less efficiently. And this, as we had a conversation with Anthony Williams, I'm glad he's here to confirm what I'm saying. The implementation may use a mutex to provide the synchronization in atomic share pointer, as we discussed. But you can manage it using making it lock-free, and you can query it with the isLock-free function that's common in all atomic variants. But with a lock-free atomic share pointer, what he's doing is he's using a split reference count for atomic share pointer. This is what is commonly used, known as a double word compare and swap. So the share pointer control block basically holds a count of external counters in addition to the normal reference count, and then each atomic share pointer instance that holds a reference has a local count of threads accessing it concurrently. What this really means is now we have a zoo of choices between all these excellent mechanisms. And what I'm here to do, and what these guys are here to do, is show you which technique to choose when. So this is a table that we worked on for over 2 years, talking to many people. And it's about, beyond performance, you also need to choose from other properties of lock-free programming. So across the top, you have reference counting, which is essentially what share pointer does. You have reference counting with double compare and swap, which is essentially what atomic share pointer does. And then we have RCU, recopy update that Paul McKenney is going to talk about, and hazard pointer that Michael is going to talk about. I've written red lines across because even though many of these properties are intertwined, you can kind of separate two properties that are a little bit of a flip coin side of each other, so that you can kind of see. So here across the top, we have things like unreclaimed objects. What do we do? In this case, RCU is unbounded. It's noticeable. Oh, I need to mention what the colors mean. The yellow color means it's a good property. The white means it's not so good. Okay? The green one means it's really good. Okay? So when you're making choices, you need to think about whether the unreclaimed objects are bounded or unbounded. In this particular case, obviously, RCU stands out as being one of the less preferable choices, because in RCU, the unreclaimed objects can be very large. But this is what turns around, it gives it forward progress, which is what the next column is about. The next column about non-blocking traversal is about forward progress on traversals. The traversal forward progress does really well is the trade-off here for RCU. for hazard point, for the next two, we're talking about what it means to have forward progress on the reclamation as well as the traversal speed. The forward progress on reclamation is identified as really good for hazard pointers because it has a fixed number of hazard pointers, and you just basically go walk through it. But in decas, okay, it is an atomic operations that can potentially fail, as I understand it. It could stop, okay? RCU is blocking is the less capable in here, is because one reader can get stuck, and so you can reclaim. So you can't reclaim anything until that reader gets unstuck, okay? And this is what gives it the forward progress guarantee property. The traversal speed for RCU can just be single thread loads. It doesn't even have to be parallel. For hazard pointer, it has an overhead per traversal pointer, which might have changed. You have to store in the hazard pointer, and then you would need to check the pointer, it hasn't changed, and make sure everyone else also see the store. Hence the store load fence in that particular case. The next area talks about reference acquisition, contention among readers, and atomic automatic reclamation. With regards to reference acquisition, it has to do with the chain of pointers that you would have to unzip if you actually finish removing one of them. It turns out that reference counting with decas and RCU do really well on these things, okay? You just do two atomic operations. It's essentially done. With decas, you might have to, I think there's potentially 6 atomic operations. One to increment the thread count, a pointer, to go to the and then it would go in and increment the reference counter, and you would have to go back and decrement the ref count, okay? So essentially, with the other two, you can tell that both RCU and hazard pointers have behaved very well with regards to high contention among readers. If you have many readers, this is where RCU and hazard pointer shines. And by the flip side of the coin, you see that automatic reclamation is better, because with reference counting with decas, it's all automatic, whereas you have to manually ask to reclaim objects in RCU and hazard pointers. So you can see that all these are essentially different sides of the same coin. There's one last part there that isn't really a big performance consideration, the domain. There are different meanings for domains for RCU and hazard pointers. They don't apply in the reference counting case. So with that, I want to conclude and ask the hazard pointer inventor, Michael, to come up, and then he'll be followed by Paul McKenney. So I'm going to see if...
Okay. So I'll continue the talk, and I'm going to talk about hazard pointers and describe the problems that it solves and how it does so, and what we're proposing for standardization. And so we'll start with a running example, a wide concurrent set. Imagine that you have like a very large memory block that you want to apply concurrent set on, and it doesn't fit in any standard like atomic operations like on hardware or supported by language. So one common solution is to, instead of like having the object embedded in place, it's just you represent it with a pointer and then copy and write whenever you change it. So every new value is just allocate a new block and you replace the old one. So this is kind of a naive implementation. It's incorrect, but a class for wide concurrent set. So you have like whatever the type is, you have the value, and you have a pointer to a node, and when you do concurrent set, you load the old value and you try, then you compare, does it contain a value that that's equal to what you expect? And if it does, you allocate a new node with a new value, and you try to do a compare exchange, and if you succeed, you delete the old one and you return true. This is incorrect because of multiple problems. When you access the value, you actually this is unsafe access because you don't know if this block is actually still there and still accessible. You're doing compare and exchange with like using a value that that you assume that it's actually, like, if it's still there, that means it hasn't, the original pointer hasn't changed, but actually it could have changed, and the meaning of that pointer has changed. So that's the ABA problem. And of course, if we just do delete P, that's, we're reclaiming without really knowing if there are other threads that have reference to that block. So that's unsafe reclamation. So I'll start by just going through going through an example of the ABA, how the ABA problem would occur in a scenario running this kind of code. So this is the same as the code as was in the previous slide, but just like condensed. And the lines in red, these are kind of the responsible lines for causing the problem. So we start by having a thread I reading the value A from the pointer P, the shared, the pointer represents the object, and the thread I will read the value U from that block A. So that's fine. It looks like we're gonna proceed to try to replace that block. In the meantime, thread J changes the value and actually allocates a new block B that has some different value W or whatever, some value W, and also thread J reuses block A to hold the value Z, which is different from U that it used to hold before. Now thread I, so thread J sets up P to A again. So now it succeeds in doing that. Now thread I comes back and allocates a new block C that holds the value V, because it's like, okay, now we are gonna try to do compare exchange on the pointer. So we're preparing the block that holds a new value. And we do the compare exchange. Yes, it's like, the pointer was holding up, was pointing to block A again. And we mistakenly assumed that actually that means that the value is still U, whereas actually we did a compare and set where the old value was Z, different from U. So I should, so this is like incorrect outcome. And the problem is that we couldn't tell if the pointer changed or not. Another problem that we'll solve using header pointers is unsafe memory reclamation, and these two lines in red are the the offending lines. So we start with like having a thread I reading at the pointer A from the value A from pointer P, and now it's about to dereference that pointer and access the contents of the node. In the meantime, another thread J sets P to point to a block B and returns A to the operating system. So now block A is unmet. Thread I comes back and has access violation. There is just it had no chance to check anything to see if it if it is safe to dereference that pointer or not. So that's kind of one case. I mean, in all these cases, ABA and memory reclamation issues, you could get like all these kind of incorrect result, corrupting your data structure, corrupting someone else's data structure, or access violation. So I'm gonna switch to describing hazard pointer, and in its simplest form, it's really very, very simple. It just a hazard pointer is a single writer multi-reader pointer, just like any pointer size location, and each hazard pointer has one owner at any time that can write to it, but then other threads can read from it. And basically, what a thread is doing by setting a hazard pointer to the address of an object is telling other threads, or itself even. I mean, so it's telling all threads that if any thread remove that object from being reachable to create new references. So now it's like if you make that object unreachable, after the last time this thread set the hazard pointer to point to it, you must guarantee that you don't reclaim it until I change the value of that hazard pointer. So that's kind of the message that is sending. And that's from the user side, the user, the one that's trying to protect objects using hazard pointer. From the reclamation side, the threads that are actually removing objects and retiring them and want to reclaim them, but they cannot reclaim it right away, what they do is, like in its simplest form, they would just like go and check all the hazard pointers. If it doesn't match any values, it's okay to free. But if that's inefficient. So you would just like read all the hazard pointers, try to collect them in some efficient structure that has like, you know, constant expected time, lookup time, and now you just have a private list that has, you know, sizable enough that you're guaranteed to to reclaim something, because you will not fail to reclaim more objects than the number of hazard pointers. There are only, like, you know, there are only that many choices of values that will prevent reclamation. So this is kind of like the algorithm's simplest form. Going back to that example, this incorrect, so we try to make it correct. And this is pseudocode. This is not C++. What I inserted there is that, like, okay, where are the hazards? The hazards are actually the unsafe access, like here, and the ABA problem over here. So before we get to, you know, the hazards, we actually set the hazard pointer to point to the block that we want to protect. And then that's where the store load fence comes to play. So in general, we want to make this lock-free. In a different context, we might not care. We might have a lock around it, and we don't need fence or stuff like that. But in this case, we want to load again the source of that reference to check that it's actually it is reachable. And by the way, this is not susceptible to the ABA problem. It's okay between these two like steps that the object is, like, you know, retired and reclaimed and reinserted. That's okay, because what matters is at this point, when we're checking that it is reachable, we know that the hazard pointer is already pointing to it. So it is protected from this point. Okay, and by doing that, then we are guaranteed that until we clear the header pointer, that we have protection that it will not be reclaimed. And if it's not being reclaimed, then it will not be reinserted. So that works for the access and for ABA problem. So this is kind of more like the template interface that we have right now. And that would look like the node would inherit from some type that, you know, adds some capabilities. And we have a hazard pointer owner that automatically acquires a hazard pointer. So it's kind of an RAII interface and a protect function that protects the value. If it succeeds, we can proceed without worrying about the object being reclaimed prematurely. When we end the end of the scope of the hazard pointer owner, it automatically clears and releases the owned hazard pointer. So this is from the user side, the user of the hazard pointer. This is for the remover's point of view. When you have an object, you don't delete it, you retire it. Basically, you're kind of handing it over to the hazard pointer library to be responsible for reclaiming it when it is safe. Okay, so I will have some time here. So the point of looking at the system, the hazard pointer system, is that you have objects in data structures or representing resources, and they can be protected by users, threads that use hazard pointers, that own and can write to hazard pointers to protect these objects, to have access to them and to protect from ABA, to have ABA safe comparison. So the removers, they have to read the hazard pointers and to decide when it is safe to move these, like to reclaim these removed objects to make them free for reuse and reallocation, or return to the operating system, or reclamation of resource. So this is kind of like system view of hazard pointers. The life cycle of an object is that it's allocated, it's reachable, so you can either like have a shared way of reaching it, or threads handing over references to each other. Basically, you can create new references. You can have hazard pointers start to protect objects. Once some thread makes the object unreachable, that no new reference can be created, then hazard pointers can continue to protect the object, but you cannot really start a new protection. And once it's retired, then yes, you can still continue to protect it from being reclaimed, but also there might be attempts to reclaim it, and they will succeed or fail depending on are there references to the object or not. Once you reclaim it, you can reallocate it if you want. I wanted to mention domains in the context of hazard pointers. A domain contains a set of hazard pointers, and these hazard pointers may protect a set of objects. So a hazard pointer would belong to one domain, because it doesn't make sense in that case to belong to multiple domains. We would have a default domain, because we don't want to bother the user to define one if they're just using the default domain. But it's good to allow multiple domains, because you can think of like two threads communicating together using data structure. Why would they bother by checking the hazard pointers of like 1,000 other threads that are doing something else using hazard pointers that doesn't apply to their the special communication between them? So it is like savings in space and time to allow multiple domains. A thread might operate in multiple domains, depends on what objects they are using at the time. I'm not going to get into too much detail of this, but it's a really multi-dimensional challenge to design to have one specification of hazard pointers, because just look, there are so many. There will be users that want different features. So I implemented this like many times, but it's always kind of customized to a certain use, so it's much simpler to do that. So here's you have domains. You have two ways to have a default domain, multiple domains. Object reclamation, you want to be able to customize that. Metadata, do you want it to be embedded with the object or separate? Hazard pointers, that's are they fixed number at compile time, at runtime, or are they dynamic and they have in a linked structure? Do you want them pre-allocated because you don't want exceptions, or so lots of options here that probably different users will want different support. Allocators for hazard pointers, for metadata, progress guarantee. It's probably more efficient to have blocking by default, but if a user wants to have an end-to-end block-free path, they should be able to do that. Thread local, that would be better by default, but they can be problematic for certain programs. So we should allow them we should allow users to have a TLS-free path. And exceptions also, we should allow the user to be able to have no exceptions end to end. So I'll skip this, and yeah, the template interface. There is a current snapshot of the interface that is public on GitHub under fully experimental. And if the user doesn't do any customization, they really don't need to know about the whole interface. They just need to know about the representation of the object that's protected by hazard pointer, and the owner type that actually kind of does RAII an interface to the actual hazard pointers. So I'll just go through the owner template as a representative of. So there's a lot of change in the interface. I should in like a couple of minutes. Okay. So yeah, the owner by default would use the default domain, and you know, it can, doesn't do thread caching. We don't copy or move the owner, because it just like it is actually good to have guarantee that the owner owns a header pointer at any time. So acquisition, at construction it acquires one, and destruction it releases it. Okay. Okay. Oh, I don't know how this. Okay. Then these are kind of the functions that are on behalf of the owned header pointer to protect the reference, to set the value, and to clear the value. And then there is a free function to swap two owners. This is good for hand-over-hand operations. Yeah, this is like if we want to customize, there's a way to customize the example I showed you for the concurrent set, wide concurrent set. I'm going to end with showing you an example of hand-over-hand traversal. So here we have a reader that is like looking for a value in an ordered single linked list, and to do hand-over-hand traversal, it acquires two header pointers. So one kind of like for the previous node and one for the current node, and hand over hand. So it starts by it has a reference to previous and current, and now it's like assuming that the previous one is already on solid ground, and now it wants to set the current header pointer to the current node. So it's always doing one in every iteration. It's actually protecting one more node and releasing protection of a previous one. So at the end, you can see here, like I skipped some parts of the loop. The code is available in publicly. So there are examples and tests. Oh, sorry, there's a typo here. It's just swap. So you see here that we set the we kind of advance the prev and curve pointers. We also do swapping the owners. So by swapping the ownership, is actually we're just swapping the header pointers that are owned by the owners, but we are not changing the values of the header pointers themselves. So it's kind of we swap them, but they continue to protect the same node that's been protecting. And at the end there, what used to protect the previous value, it becomes kind of free now, that we can reuse it in the next iteration, but it is called under the current owner. And that's kind of that can be as simple for a user to use as if they don't need any customization. I'll leave it. Okay, I'll hand it over to Paul to talk about RCU. Okay.
All right, we're here. So this is just the RCU part, and this is just a quick rundown of kind of RCU's philosophy. The idea is we have a way of publishing new data into a data structure, and there's an RCU assigned pointer thing that does that, and there's things built on top of that for lists and other things. And a reader can subscribe to a given version of a given pointer with RCU dereference, and again, there's ways of handling lists and other things like that. And the big deal, this is very similar to hazard pointers, you have to have a way of waiting for all the people that might be interfered with by an update, by a destructive portion of the update. And here, what we do is we define a reader. With hazard pointers, the readers are associated with each object. And that's why they have a small number of memory, because they identify each and every object, same with reference counting. Here, what we do is we identify a range of code and say anything that thing reads, it might read. And that gives us the speed and the weight freedom, but it means that we could have a lot of objects hanging out. So we identify with RCU read lock beginning and ending with a matching RCU read unlock. They can be nested, and anything in there is a reader. Of course, you might want to say, where's the RAII? And we'll get to that with a later slide. But this is where we started from. And an updater is going to have to wait for all the readers that are already in their read side critical section, that have already executed their RCU read lock, to get to that matching RCU read unlock before they can proceed, and that duration of time is a grace period. The easiest way is you say synchronize RCU, it blocks, and then when everybody's done, you resume again. Unfortunately, there's a lot of algorithms that don't like waiting, And so we have an asynchronous form called RCU, where you pass it a function and a pointer to the object, sort of. And that one, as we'll see later, causes a little bit of trouble in C++. But we'll get there. Fortunately, I've had some help from a number of people, so with even more help, I might get there. This is insertion, and it's just how we get things inserted. This is a very simple data structure. This is the 4 states like Michael Wong had in his presentation. And we allocate something, that's the 2nd state. We initialize it, that's the 3rd state. And if your memory allocator is working, nobody else can have reference to that, so you can do whatever you want. That's why it's colored green. As soon as you use RCU assign pointer to make that pointer point to your new object, bang, all of a sudden the readers might be there for any length of time at any time without telling you about it. And so from then on, you have to be careful. So we have to remove. And this looks very similar to what Michael Wong showed you for reference counting. It's just the operations are different, but it's the same process and the same sort of a thing going on. We remove the cat. We use C++ atomics, or we can, to make sure that the readers either see the pointer to the cat or the pointer to the GNU. But either way, they see a valid list. They don't see some mush of the 2 pointers that you might get if you fail to use atomics. Then you synchronize RCU, do a synchronous wait for all the readers. Once all the readers are done, well, the old readers might have a reference to the cat. Any new ones, there's no way for them to get to it. So once all the old readers are done, nobody's looking at the cat except the updater, and it can do whatever it wants with it, including free it. But as Michael pointed out with reference counts, same thing with RCU. We can have 2 simultaneous things. Michael talked about a veterinarian, and there they are. If we have a cat that's heartbeat happened a ways ago, the 2 veterinarians might disagree about whether the cats are alive or dead. And this, again, is anything you're representing inside the computer that's outside the computer. There's always uncertainty about what happened in what order and what is really finished. For example, if you suddenly can't access the memory stick break, or are things just slow? It's the same decision is really generally applicable across anything where you're interacting with an outside device. All right. That's just putting up there saying you can make a really, really simple thing that acts like RCU. This is what a reader looks like in C. So we have that RC read lock at the top that starts the critical section. We could pick up a pointer. And the nice thing is that whatever pointer we picked up, it's guaranteed to still be around. Somebody might remove it from its data structure, but it's not going to be freed until we get to that matching RCU unlock down there at the bottom. We can do whatever we want with that pointer, with that object. It'll still be in memory. It's not going to be reused. There's no ABA. It's there. And of course, that's why we have so much storage outstanding, because it has to leave everything that might be reached there as well. But as soon as we hit that RCU unlock, that thing might be freed immediately. Okay? But the nice thing is those primitives are all very lightweight, and the updaters do something very similar. They probably, if you have multiple updaters, they might use a lock to exclude each other. They might pick up the old pointer, make the put the new pointer in there, which they presumably initialized up earlier. And then once they release the lock, they can wait for the grace period. Once synchronized RCU returns, they know for sure there can't be any reader referencing that old thing that they just yanked out there. Therefore, they can just free it. Okay? So the same structure again as the reference counts. The difference is, as noted earlier, is we have to tell RCU with the synchronized RCU, hey, we're interested in freeing this thing. With reference counts, it would happen automatically. Okay. This is a view of what a grace period kind of looks like, sort of schematically. We change something, we wait for a grace period in yellow there, and the grace period has to extend long enough that any reader that was there before the grace period started, so you can see there's 2 of them that really did, that grace period has to continue until those readers get done. Once we get to the green portion, any reader that might see the state beforehand, they're completed. Okay? So that's just kind of a diagram of how this looks. You could draw a similar diagram for reference counters or hazard pointers if you wanted to. Now, you can go longer. If the grace period runs long, no big deal. There's some memory that hasn't been freed. Okay? If you start the grace period late, that's still okay. Because any reader that was there at the early grace period is either there or gone by the time you get to the late grace period. You may wait a little longer than you need to, but things will work. Nothing will break. And this turns out to be really important because if you delay the start of the grace period, you can make the grace period cover multiple changes. So those two, if we just started right when that first change was done, we'd have to have 2 grace periods, do the work twice. Because we waited, we were lazy, we were rewarded, we had to do less work, it covered both guys, and that means our per update overhead is less and life is good. And we do that a lot. In fact, we do it pretty viciously. We start it later, we amortize out, and it's not hard to do something in the Linux kernel, like make a big tarball and then remove it, and have literally thousands of updates using the same grace period. So it's a very good labor-saving device. However, that means if you increase the length of the grace period, you're going to have longer grace periods, you'll wait longer. And you also increase the memory usage, which of course is one of RCU's potential disadvantages if you have a small memory machine. So this is a design trade-off, but that's the design trade-off RCU has chosen. Okay, now let's get to the kind of the fly in the ointment from a C++ standpoint. We have this call RCU thing. And what it's doing, you pass it an RCU head, which is normally embedded in your data structure. And that allows RCU to track all the stuff that's waiting for a grace period. Just links them all together. And you also pass it a function. And that function is going to be called at the end of grace period. So diagrammatically, it looks like this. So we had a change. Right when the change is done, we do call RCU. We hand it the pointer to that RCU head structure. We've handed a function. When the grace period is over, that function gets called and it's passed that RCU head pointer. Works fairly well. We've been doing it for a very long time. In fact, in Dynix PTX in the 90s, we had this, but we didn't have the synchronous wait. Okay. The problem is, what you'd like, and it happens a fair amount of the time, but not always, what you'd like is you'd like the shape of that function, that thing, to be known at compile time. And you'd like it at least to be known at construction time, all right? But no, a fair amount of time is not known until you actually do the call RCU. Because what you want to do may depend on the state of the system. For example, you might have in the Linux kernel, you might have a file. It might start off not having attributes. And you're using it, and somebody slams attributes onto it. And then when you want to get rid of it, you may have to do something different as a result. And you certainly didn't know that at construction time, let alone compile time, what it was going to look like. Because at that point, it was out on a disk somewhere. It might not have even existed yet. Okay? So sometimes we can do it, just have any arbitrary thing, lambda capture and all that stuff potentially. But there are cases where that, and I found it with lots of error message, where it does not work. Okay? When F is only known at call RCU time, you have to have a fixed chunk of storage to put that function pointer in there. Okay, well, C++ has a lot of other things you could use, but there's another complication. And this is, the problem with this stuff is I've been doing this for 20 years, so it's not here, it's kind of down here somewhere. And so we had a Korean barbecue that helped bring it up to my brain instead of my fingers a couple nights ago. And as the title says, any type, any time, any translation unit, anywhere. I mean, RCU just gets this stuff dumped on it, and it has to deal with it. And so we've got the 6 boxes there representing 6 different translation units. Each translation unit has 4 instances. And the little A1, B1, so on, those are the types. So for example, translation unit C in the middle on the top there has 3 instances of C1 type and 1 instance of C2 type, all right? D in the middle on the bottom just has 4 instances of the same type. And these have been handed to RCU to clean up in some order. And the gray lines show the order it has them on this list that it's keeping track of. And you can see this list just is wandering through the translation units kind of randomly. And it's got all different sorts of types. And if it's off somewhere, it does have no idea what these types are. The only way it can correctly interpret the types, well, there's 2 ways. One is you get an inheritance from an abstract type and have a virtual function pointer, which may not be what you want if you have performance critical code. The other way is you have to get the execution into the translation unit somehow. Okay? So one way or another, you have to get some kind of hook to get something back into the translation unit that knows what the heck this stupid thing is. And right now, we're kind of at a point where we have to have some kind of a function pointer to do that. There may be something come up with a better way, but that's where we're at right now. Okay, so this is the C language API for RCU. I'm only going to worry about the top 4. RCU read lock, RCU read unlock, synchronize RCU, and call RCU. We've gone through those. That's just their templates. or their prototypes, I should say. And you can define an RCU domain with a current proposal, and they're kind of down in the middle. I apologize for that, but you can see that there's a read lock, read unlock, synchronize, and call, and those are just member functions, which allows you to have a domain, kind of like the hazard pointer domains, but usually used for a different purpose, that allows you to have a single translation unit deal with different types of RCU or different domains of RCU it wants to. We talked about wanting scoped readers. This is a API for doing that, so that you can say this block is reading, and then however you exit it, it'll stop reading when you leave. I did something for call RCU, and I presented on Wednesday, and the less said about that, the better. Isabella provided a version. This one requires you to know the shape of the function kind of at construction time. And it seems to work. She gave me some code. I've integrated in it. Passes tests, and that's good. And Arthur O'Dwyer did another one that allows you to pass the thing in at call time. So you pass the destructor object, he says, at call time. And it may be we want both of these because, you know, if you can do it at compile time, you can use value capture lambdas, for example, which you certainly can't unless you want to allocate on the free path, which I definitely do not. That's a good way to deadlock your system because it needs to allocate memory in order to free it. It's not got any memory. That's why you're trying to free the memory in the first place, and I don't like that, okay? And if you like it, you can derive your own subclass and do it yourself, all right? This is just performance comparison. Unfortunately, I don't have Mercurial installed, so I wasn't able to grab Anthony's thing to put it in there, but we'll get there, okay? I was trying really hard to make Git pull a Mercurial archive and wasn't sure why it was yelling at me. I eventually sent him an email and he says, look, you need to use Mercurial. I go, okay, fine. Anyway, this is a specialized technique. You use it where it makes sense. The Linux kernel community tends to be a little bit contrary. So I told them, don't use it down there, and so far they've come up with 2 cases where you actually should use it down there. Maybe they'll come up with more, but for the most part, you want it to be in the case where the veterinarians might disagree, and that's okay, all right? And if some agreement is needed, you can impose it in various ways. Okay, anyway, this is kind of our future things. I'd like to invite Maggot and Michael Wong to come up here, and we've got a couple minutes for questions. As Michael said, we want to get these things into the concurrency TS and thence perhaps in the C++ standard, maybe even in C++ 20. We have some working drafts, hazard pointers you can see there. We've got an old version of memory order consume, and I've got 2 papers which I have written up with things that I need to send to John Spicer? Yeah. Thank you. John Spicer to get numbers for, and those should be available for perusal in a little bit. Questions, comments, thoughts, tomatoes? Wow, okay. I think I saw you first, then you, then you. So please come up. Okay. There's a microphone over there. We have implementations in user space that work in all sorts of environments. Go ahead.
So those implementations in user space,
Mm-hmm. Right.
Do those points still stand for the user space preemptive?
They do, for most of them. They do for all of them, actually. So what happens there's some user space RCUs that require heavier. Oh, I'm sorry. The question was, hey, we've got a bunch of different user space RCU things. They have different properties. Do they all really fit that table that Michael Wong presented at the end of his presentation? And the answer is yes, there are some slight variations. For example, for all of them, when you traverse to a new object, it's the same. You just use a normal load instruction on the machine. There's no memory barriers, no nothing. However, to your point, RC read lock might have some overhead. For example, if you use the QSBR, the quiescent state, you can blame the US Unit of Toronto guys for that one, they named it. Quiescent state-based reclamation, there we are, QSBR. If you use that, RC read lock and RC read lock are just free, just as they are in non-preemptive Linux kernel. There's another one that has explicit memory barriers or store load memory barriers, but rather than being on each traversal, as you'd have with hazard pointers, they're only on the RC read lock and the RC read unlock. Of course, if you have one traversal, you're better off with hazard pointers. Anyway, I'm sorry about the rest of the questions. I just got the session is over sign, but we'll be around for at least a little bit longer, and there's a break coming up at some point, and we'll go from there. Thank you all very much for your time and attention, and have a great rest of the conference.